Okay, so this is the fourth video I'm recording for 2021, and again we're looking at a review of things that you should by now be pretty familiar with. Certainly for my students, this work was set as holiday work, and so this video is purely as a resource to refer to. We teach polynomial algebra certainly, but polynomials pretty extensively at both Year 10 in Semester 2 and Year 11. And so by now this should be pretty routine, and we would prefer to free up our time in Unit 3-4 methods for other newer things. If, however, you are a bit stuck on some of this, or you haven't learned it as well as you could have over the last couple of years, I will link in the description box the videos to, I've got some videos from my Year 10 class in Semester 2 last year that I will link. There'll also be some going up throughout the next couple of months with my Year 11 class this year as well, so plenty of resources to refer to if you need more detail here. Okay, so polynomials are functions of the form, and this is a slightly, technical definition, because we do tend to write polynomials from the highest power down, so it's a bit complicated. Also, the A0s and A1s tend to confuse people, but really, just a constant term plus a coefficient times x plus a coefficient times x squared plus a coefficient times x cubed plus all the way up to an x to the power n term depending on the degree of the polynomial. Obviously any of those coefficients could be 0, so a cubic, for example, which would be a polynomial where the highest power of x is 3, doesn't have to have the constant term and the x term and the x squared term and the cube term. It could have just 2 or 3 or even just one of those terms, as long as it has an x cubed. So as I said, A0, A1, A up to an are the coefficients of each of the terms. The term with the highest power of x is referred to as the leading term, and the positive integer n is the degree of the polynomial. So the highest power is the degree of the polynomial. And we usually write our polynomials in descending powers of x. So we're pretty familiar with, and the last few review videos have covered the first two types of polynomials. So a linear function is the most basic kind of polynomial. Highest power of x is 1. A quadratic function we're pretty familiar with now. Highest power of x is 2. And through the when we talk about polynomials in this course, we're generally referring to cubics and quartics, and obviously higher degree polynomials as well. But yeah, the techniques we introduce for cubics, they then apply for all polynomials beyond. Okay, let's just have a look at some theory and some examples. So the first concept is this idea of equating coefficients, and it's really about what makes two polynomial functions equal. So if two polynomials are equal, two things have to be true. They must be of the same degree. So a cubic is not equal to a quadratic. I mean, that's an equation that can be solved, but those two things aren't equal things. So they have to be of the same degree, and all the corresponding coefficients must be equal. So an example of how we might use this would be something like this, where we want to find the values of a and b if 2x squared plus 12x plus 14 is equal to a times x plus 3 all squared minus b. Now essentially you really need to focus on getting both sides of the equation in the same form so that you can then equate the coefficients. So you've got two options really. The left hand side, in order to get it in the same form as the right hand side, you would need to complete the square on the left hand side. So, personally that wouldn't be my preference. To get the right hand side the same as the left hand side, we could just expand out. So I would probably expand out the right hand side, but equally it would be possible to get the two functions, polynomial functions, in the same form by completing the square for the left hand side. Obviously if this was a cubic, we don't have a tool like completing the square available to us though. So I'm going to expand out the right hand side. So we're going to have that 2x squared plus 12x plus 14 is equal to a times, now that perfect square, x plus 3 all squared is x squared plus 6x plus 9. Take away b. Sorry, I hate b, it often looks like a 6 in handwriting, so I'll try to be a bit careful about that. So expanding out this bracket, we're going to have a times x squared plus 6ax plus 9a plus b. And now we're in a position to equate the coefficients. So what I mean by that is the coefficient of x squared on the left-hand side must be the same as the coefficient of x squared on the right-hand side. The coefficient of x on the left-hand side must be the same as the coefficient of x on the right-hand side. And the constant term on the left-hand side must be the same as the constant term on the right-hand side. So we get from the coefficients of x squared that a has to equal 2. The coefficients of x tell us that 6a has to equal 12, which is the same as a equals 2, so we haven't learned anything new there. The constant terms tell us that 9a plus b must be equal to 14, and we know what a is. A is 2, so it's 9 times 2 plus b has to be 14, so 18 plus b equals 14, and so b must be negative 4. So the question, find a and b, so therefore a is 2 and b is negative 4. As I said, you could complete the square for the left-hand side and equate a and b in that regard. You can probably see pretty quickly that a is going to be 2, just because clearly when we expand all this out, we're going to get ax squared. So one of those two options. Get them in the same form, and then you can equate the coefficients. Okay, the second technique we need here is polynomial division. As I mentioned earlier, if this is a fairly new thing to you, or if this doesn't feel at all familiar and you don't remember this at all, please go back and watch an earlier video where this is explained in more detail, and the steps I'm doing are sort of reasoned through so that it makes sense. It's not just randomly shuffling numbers about. But hopefully this is something that's pretty familiar, and we should be able to just refresh our memories by launching into one example. So we want to divide the cubic, 3x cubed plus 16x squared plus 12, by a linear function, x minus 1. So I do it as long division. There is an alternative process called synthetic division, which I know some teachers teach. Personally, I still prefer to do long division. I find it works better when you've got you're dividing by terms like 2x minus 3, where there's a coefficient of the x. I find it's the same if you're dividing by, a quadratic term, whereas you can't divide by a quadratic term with synthetic division. So I do think it's important that you have the long division technique in your toolkit, but the synthetic division technique can, some people think it's a lot more efficient. And look, it is quick in that you write down less, but actually you are essentially doing the same calculations, just you're only dealing with all the coefficients, not with the actual x cubed and x squared terms. Anyway, so we're going to divide I'm going to do long division. We're going to divide x minus 1 into the cubic 3x cubed plus 16x squared. Now it's really important, in the same way that when we do, dividing numbers, doing 306 divided by 5 is not the same as doing 36 divided by 5. We can't just omit a term, a digit in a number because it's 0. So the same thing happens here. There's not an x term, but I'm going to just write 0x here, just so that we're maintaining that place value. There is a column for all the x terms. Otherwise, if we didn't do that, we would have problems in the subtraction steps as we work through our long division. So any missing terms need to be added in. Make sure your terms are in decreasing powers of x. Okay, so then the first thing we do is we ask ourselves, what would I have to multiply x by to get 3x cubed? Technically what we're actually doing is, what is 3x cubed divided by x? But in many situations it's actually easier to think about it as, what would I have to multiply x by in order to get 3x cubed? So that would be 3x squared. And then I take the 3x squared here and I multiply by x minus 1 and I write it underneath here. Okay, so 3x squared times x is 3x cubed, and then 3x squared times negative 1 is negative 3x squared. Alright, then we subtract, and these should cancel out the cube terms because that's how we designed it. We chose the term at the top that would ensure that when we multiplied it by x, we got 3x cubed, and so therefore we're eliminating the cube term. So 16x squared minus 3x squared, so that's going to be 19x squared. Then we bring down our next term, plus 0x, and we repeat the process. What would I have to multiply x by to get 19x squared? So that would be 19x. I take the 19x and I multiply it by x minus 1, so we get 19x squared minus 19x, and then we subtract. So as I said, you should see again that the x squared terms now cancel out. That's how we designed it. and we now have 0x minus 19x, that's plus 19x. So if we hadn't written in the 0 here, we would be trying to do 12 minus negative 19x, so we're not subtracting like terms, so you want to make sure that you've got like terms. Each column only has, you know, a specific kind of term. And then finally we bring down our 12, and we are then asking ourselves what would multiply x by to get 19x. That's going to be 19. Multiplying 19 times x minus 1 gives us 19x minus 19, and we subtract 12 minus 19 is 12 plus 19, which is going to be, what's that, 31. Okay, so we've got a remainder here. Now, this won't happen if we're doing long division as part of a factorisation, but this can happen if we're just dividing two things. So when we think about division, if you're doing, for example, you know, 15 divided by 4, well, 15 divided by 4 is 3 with a remainder of, let me make it a different number, so it's not, let's do 15 divided by 6. It is 2 with a remainder of 3, okay? So we write that as 2 and 3/6, which is 2 1/2. And so the same thing is going to happen here, okay? So when we do, we've done 3x cubed plus 16x squared plus 12, and we've divided that by x minus 1, and we found it went this many times whole. We call that the quotient, okay? And then we've got our remainder down here. So this is the quotient. So in the equivalent to the number thing, that's equivalent to the number 2, okay? It goes, when we divide 15 by 6, it goes 2 times whole. So the quadratic up the top there is the number of times it goes in whole. So that is 3x squared plus 19x plus 19 with a remainder of 31. Now when we had a remainder of 3 here, to express that as a fraction, we do 3 over the thing we divided by. So this is going to be plus, now remember when we write mixed numbers, that's really a plus in there. It's not multiplication. So it's plus our remainder divided by the divisor, which is x minus 1. Okay. To perform polynomial division using CAS, you won't really need to, because the main reason you're going to be doing polynomial division in methods is because you're trying to factorise a cubic or solve a cubic, in which case you would just use your CAS to factorise or solve. You wouldn't actually do the long division. However, it is possible to get your CAS to do a division. So if I just type in this division, you know, there's nothing special about it. There's no special instruction for divide. You just type that divided by that. So if I type that into my CAS, 3x cubed plus 16x squared, oh sorry, should have put it in a bracket, but I'll do it at the end, plus 16x squared, or I should have done a, let me give myself a fraction, there we go, so 3x cubed plus 16x squared plus 12, and we divide that by x minus 1. If we just press enter, it won't do anything, okay, because it doesn't go whole. If x minus 1 was a factor and it did divide in, then it would tell me, it would do the division, okay. The issue here is because this doesn't actually divide, it leaves a remainder, and so it just leaves it as essentially an improper fraction. So a top-heavy fraction, a cubic on top of a linear function. The way we can force it to do the long division is to tell it that we don't want an improper fraction, we want a proper fraction. So we use the fraction tools, which are available in both the number and algebra menus. So so menu 2.7 is where you get fraction tools, or menu 3.9 fraction tools. They're exactly the same tools, it doesn't matter where you get them from. We've got things like proper fraction, common denominator, etc. Proper fraction is something I use a little bit actually. It can be handy when you're dealing with equations for hyperbolas where the function's written in a sort of non-standard form. Anyway, we'll get to that further on. And so forcing your CAS to write it as a proper fraction will force it to actually do the division, even though it results in a remainder. Okay, remainder and factor theorems. Again, I'm just going to give these to you here and look at how we use them. If these are completely unfamiliar ideas to you, I really encourage you to go back and look at an older video that actually explains what's going on here. So if a polynomial, p of x, is divided by a linear factor, ax plus b, then the remainder is given by p of negative b on a. So the way we just work out what we need to substitute into the polynomial, that was a highlighter. the way we work out what has to go in here is we take our linear factor, we make it equal to 0, and we solve for x. Okay, so if you solve ax plus b equal to 0, that means we get ax equals negative b, x equals negative b on a. That's what I need to sub in order to get to work out the remainder. The factor theorem is then just an extension of the remainder theorem, because we know if something is a factor, it leaves no remainder. So if ax plus b is a factor of the polynomial p of x, then that means that p of negative b on a, which is the remainder, has to be equal to 0. Okay. So let's do a couple of examples. Find the remainder when 3x to the power of 4 plus 5x cubed minus x plus 4 is divided by 2x minus 3. Now, in my experience, students read this and they do the long division. You don't need to do the long division. If you only want the remainder, you just use the remainder theorem. So what are we going to need to substitute in? Well, if I solve 2x minus 3 equals 0, that's 2x equals 3, so x equals 3 on 2. That's what we need to substitute into our polynomial. So the remainder is going to be given by p of 3 on 2, which is 3 times 3 on 2 to the power of 4 minus 5 times 3 on 2 to the power of 3 minus 3 on 2 plus 4. And yes, we've got some fraction work, but you need to be able to do that. Okay, so it is 3 times 3 to the power of 4 is 81, and 2 to the power of 4 is 16, minus 5 times 3 cubed is 27 on 2 cubed, which is 8, minus 3 on 2 and plus 4. Okay, so 3 lots of 81, 3 80s are 240, and 3 1s are 3, so 243 on 16, minus 5 27s, well 5 20s are 100, and 5 7s are 35, so it's 135, minus 3 on 2 and plus 4. Okay, so we're going to need a common denominator to put all of that together. Lowest common denominator here will be 16, so 243 on 16, minus, we need to double the numerator and denominator here, so that's 270 on 16, minus, oh sorry, that shouldn't be a minus, that should be a plus, so plus, 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 plus. Minus, so denominator of 16, so we need to multiply top and bottom here by 8, so 24 on 16, plus, and that's 4 over 1, so we need to do 4 times 16, again 4 10s are 40 and 4 6s are 24, so 40 plus 24 is 64 on 16, it's 4. Alright, nearly there. So again, you want to be a bit strategic, so think about what you might be able to group together to make the calculation easier. So negative 24 plus 64 is 64 minus 24, so that's going to be 40 on 16. So, you know, if you can think about those sorts of things, that can help. So what have we got? 243 plus 270. Okay, so 70 plus 43 is 113, and then we've got plus 200, and sorry, I lost my train of thought there. What did I say? 43 plus 70 is 113, and then plus another 400 from the two lots of 200, so it should be 513. Sorry, I was just checking I hadn't copied something out wrong there. 513 on 16, and then we've got another 40 on 16 here, and so we've got 553 on 16 for our remainder. Okay, part B, x minus 1 and x minus 3 are factors of this quartic. Find the values of a and b. Okay, so if we know that they're factors, we can use the factor theorem. So if x minus 1 is a factor, that tells us that p of 1 must be equal to 0. So we can use that to form an equation with a and b in it. P of 1 is going to be 1 to the power of 4 plus a times 1 cubed minus 13 times 1 squared plus b times 1 plus 24. So just subbing 1 into the polynomial, and that has to equal 0. And then we can tidy that up a bit. So that is going to be a plus b, let's see, 1 minus 13 is negative 12, and plus 24 is positive 12. Alright, equation 1, you can move the 24 to the right hand side if you want. And then p of 3 equals 0, because x minus 3 is also a factor, So subbing 3 into the polynomial, 3 to the power of 4 is 81, plus, that'll be 27a, minus 3 squared is 9, and 9 times 13, 9 times 10 is 90, and 9 times 3 is 27, so 117. And then plus 3 times b, plus 24, and that has to equal 0 as well. Okay, so again, tidying this up, so we've got 27a plus 3b. I'm noticing they're both factors of multiples of 3, sorry. So if my number value is also a multiple of 3, I'll simplify my equation before I go on with the simultaneous equation solving. Alright, so we've got 81 minus 117 and plus 24. Maybe we do 81 plus 24, which is going to be 105. So we've essentially got 105 minus 117, so it's going to be negative 12. Alright, so yes, nice common factor of 3 there. Let's simplify. So it's 9a plus b minus 4 equals 0 as equation 2. Okay, so if we subtract these equations, the b's will eliminate. So let's do equation 2 minus equation 1. So 9a minus a leaves us with 8a. b minus b cancels that out. Negative 4 minus 24 is negative 28 equals 0. Oh, sorry, I've just realised, I'm pretty sure I said the right thing earlier, but I've written down the wrong thing. So in equation 1, sorry, that shouldn't be a plus 24 there, because it is 1 minus 13, which is negative 12, plus 24, which is positive 12. Sorry. Sorry, I knew that answer wasn't quite right. Alright, so again, we're doing equation 2 minus equation 1, so negative 4 minus 12 is minus 16, okay, and that has to equal 0. So we've got 8a equals 16, and so a equals 2. And then we can substitute that into our equation, back into our equation. I'll go back into equation 1. So we're going to have 2 plus b plus 12 equals 0, which means b is going to be negative 14. Okay, that's a fairly common kind of factor and remainder theorem problem, essentially using what you know about the factor and remainder theorem and what you know about factors or remainders of a particular polynomial to find unknown coefficients. Okay, so then factor theorem, remainder theorem, and long division or polynomial division of some sort go together to allow us to then factorise polynomials, particularly cubics and above. So we want to fully factorise this particular cubic here. So the first thing you need to do is identify one factor, so that then you can use long division to find the other factor, or polynomial division, whatever version you do, to find the other factors. There's also there's long division, synthetic division, and there's also a, I don't know what you would call it, but it is technically sort of a trial and error kind of method, but you can sort of work it out by just thinking about the expanded brackets. So you might use that technique. As long as you have a way of dividing polynomials, I've got no issue with what that method is. Okay, so we want to identify one factor. So we want to use the factor theorem here. So we want to use this idea that if we sub something into the polynomial and it gives us 0, that's going to enable us to work out what the factor is. Okay, so we're essentially using this statement in reverse. If ax plus b is a factor, then that equals 0, but we can also say if p of something equals 0, we can then work back to work out what the factor must be. Okay, so start substituting things in. I always start with 1, I use it as a guide. Do I need to go much bigger? Do I think it needs to be negative? Whatever it might be. P of 1 is going to be 1 minus 7 plus 2 plus 40. So that's definitely not 0, it doesn't matter what it is, but we're not seeing enough negative terms to balance out the positive terms. We've got positive 43 there and only negative 7. So that makes me think I might need a negative, because if I only got one negative term, this one, that might not be enough, particularly with the quite big constant term at the end. So maybe if I try p of negative 1, so negative 1 cubed is negative 1, negative 1 squared is still positive 1, so that keeps that as negative 7. This term now also becomes negative, plus 40. Okay, so we're on the right track because we've got 3 negative terms now to try and balance out the 40, but those 3 negative terms aren't big enough. So let's try negative 2. Negative 2 cubed is negative 8. Negative 2 squared is positive 4, so times negative 7 is negative 28. And negative 2 times 2 is negative 4. And I think that's going to work, isn't it? Negative 36, negative 40? Yep. So when we add 40, that's going to give us 0. Okay, so if p of negative 2 equals 0, that means that x plus 2 must be a factor. So now once we've found one factor, to find the other factors, we want to divide that factor into our polynomial. So we're going to divide x plus 2 into x cubed minus 7x squared plus 2x plus 40. And away we go. So what do we multiply x by to get x cubed? X squared. Multiplying x squared by x plus 2, so x cubed plus 2x squared. Subtracting, negative 7x squared minus 2x squared is negative 9x squared. And bring down our next term. What do I multiply x by to get negative 9x squared? Well, that's negative 9x. Multiplying negative 9x by x plus 2 is negative 9x squared minus 18x. And subtracting. So 2x minus minus 18x is 20x. Bring down our next term and repeat. What do we multiply x by to get 20x? Well, that's 20. 20 times x plus 2 is 20x plus 40. So this is looking good because they're going to subtract to give us 0, which means we get no remainder, which is what we knew by when we worked out that x plus 2 is a factor. If we didn't get a 0 remainder there, either we've identified the wrong factor or we've done something wrong in the long division. Okay, so we now know that x cubed minus 7x squared plus 2x plus 40 cubic is equal to x plus 2 times x squared minus 9x plus 20. So we want to fully factorise. If we can factorise this quadratic further, we need to do that, and in this case we can. It's a simple quadratic. Factors of 20, positive 20, that add up to negative 9 is going to be negative 4 and negative 5. And so there is our fully factorised polynomial. Now again, being clear on what the various words and instructions mean, this question doesn't ask you to solve. If you were to go on from this point and tell me that x equals negative 2, x equals 4, and x equals 5, that's not right. Okay? The only way this line is true is if this equals 0. And there is nowhere here that tells you that this polynomial is being made equal to 0. Okay, so please make sure that you understand, you don't just launch into these processes and then automatically just magically stick a equals 0 here and end up with solutions. You're being asked to factorise the polynomial. Here it is fully factorised. Okay, so some various polynomial practice, long division, factor theorems, remainder theorems, possibly also some solving on from there. So once you factorise, the solving is the simple steps that I just crossed out. And yes, yeah, so exercise 4C and 4D.